In our last video, we ended with this chemical equation right here, and in this chemical equation we have NH3 that acts as a base. Now, NH3 I said was ammonia, and turns out ammonia always acts like a base. So if you see that, you know that it's going to be a base. But what kind of compound is that, right? There's no metal in it, so it must be. It's not an ionic compound. It's got to be a covalent compound, right? And so if covalent compounds can behave as bases. However, most of the acid-base reactions that we're going to look at, the base will actually be an ionic base. And so let's consider that. Let's consider these acids and ionic bases reacting together and kind of see what that would look like. You are going to have to know your polyatomic ions in order to recognize these. That's going to be helpful. But let's just look at a quick example. Let's say we have hydrochloric acid, which is going to be aqueous. It's in a solution. And we have sodium hydroxide. Now, this is where knowing your polyatomic ions is going to be important, right? I need to recognize that as the hydroxide ion. And what it produces when it combines, when these react together, is we get water as a liquid plus sodium chloride, table salt, right, NaCl, as an aqueous solution, okay? And so it may not be obvious if you're looking at this, it may not be obvious what's happening with the hydrogen, right? How do we identify the acid? We're looking at which one's donating the hydrogen ion or the proton, right? The H plus ion or the proton, and we're trying to figure out which one's receiving the H. And so in order to see this more clearly, I'm going to rewrite this, and I'm going to break up the base into this is our acid, like we said, and this is our base, and you can see it a little clearer if we break up our base into its individual ions. All right, so NaOH is made up of a single sodium ion and then the OH negative polyatomic ion, right? And so what we have over here on the right side of the equation is H2O plus Na plus, we're going to break up the ionic compound that's over here as well, plus Cl negative, okay? Now when you look at it this way, it should be then pretty obvious which one's actually getting rid of the H, right? This HCl donated an H that ended up here with the OH, and becomes H2O over here on this side, right? So the H plus combined with the OH negative hydroxide ion and formed water. And the result on the other side was water, and then NaCl, right? This sodium chloride right here. Notice what happened. The Cl was part of the NaCl. That was part of the. I'm sorry. This was the acid. This is the base. Why is that the base? Because the Na, the base is the proton receiver, and so it's the one that got, it's the proton, the acid donates it, the HCl got rid of it and gave it over here, okay, to the hydroxide ion that's part of this NaOH, and so that's why that's the base. So anyway, sometimes breaking it down, when you have ionic compounds in there, breaking those ionic compounds down and splitting the ions apart might help you see that a little more clearly. You see very clearly that we've got this Cl that had an H as a part of it over here, and it got rid of it. So that HCl's got to be the acid. Now, notice the Na plus, it doesn't change. We've got a single Na plus on one side and Na plus on the other side. We have a special name for that. We call those spectator ions because they're not really part of the reaction. It's just, they're just kind of hanging out, right? And observing everything. They're spectating. So if you hear that term, that's what I'm talking about there. Now, we can just make a list here of things to look for when we're recognizing the acids and bases. So let's just make that list real quick. And these are some rules that you can follow that are that are going to be a helpful way to recognize acids and bases quickly. Number one, if it's an ionic compound that contains the hydroxide ion, it's going to act like a base. All right, that's what we had in the last example. So an ionic compound with the hydroxide ion, and remember that hydroxide ion is OH negative, is a base. You don't have to question it. You don't have to wonder whether or not it is. If it's got the hydroxide ion, it is a base. Also, NH3, I've already said this. NH3, which is the chemical formula for ammonia, will always act as a base. So if you see that, just label it a base. You don't have to figure out anything that's going on with the H's. Finally, if a covalent compound if a covalent compound, sorry, I lost my covalent compound starts with H, it often acts like an acid. Now that's the usually one, right? It often acts like an acid. We've already seen an example where H2O, covalent compound that begins with H, in one reaction it acted like an acid, in another reaction it acted like a base. So that's not foolproof, that last one there. But if all else fails, that's a way to kind of guess whether or not which one's the acid and which one's the base in a reaction. Now, just so that you know, we can have what we call a polyprotic acid. And if you just think about that name for a second, it makes sense what it's talking about. Poly meaning many, right? A polynomial is or polygon is a multi-sided figure. A polynomial is a mathematical equation with multiple terms in it. And so poly meaning many or multiple, protic having to do with the proton that this acid donates. So this is an acid that's going to donate many, more than just one proton. So an acid that can donate more than one H plus. All right, so again, be aware of that term. We'll work with some acids where more than one H plus is donated. However, for this class, you can assume that our bases will only accept one. So let's see. For this class, bases will only accept one H plus. So that'll make things a little bit simpler. And just to kind of see this in action, let's see, where do we do that? Example 11.2 somewhere. Okay, all right, yeah, let's just go on to that example. Example 11.2, we're asked what is the chemical equation for the reaction between H2SO4, and NH3. All right, NH3. So they're asking us for that chemical reaction. What's going to happen? Now, we know, based on these rules here, based on rule number 2, NH3 has to be our base, right? So this is our base. And this guy has got to be our acid. We could have guessed that based on rule number 3 because it is a covalent compound that begins begins with an H, right? And so what's going to happen? Well, this acid has 2 H's in it, so it's going to donate both of those H's. But what did we say about our base? Our base can only receive one, right? So what's going to happen on the other side here? If our base here receives an H plus, it's going to now be NH4 plus, because it only could receive one of those guys, right? And then what's going to be left over? Well, this guy got rid of its H2, so it's just a sulfate ion all by itself. Okay? The only thing you got to pay attention to is this thing's got to be balanced. And so is it balanced? Well, we've got single N, H. We're missing an H. Do you guys see that? We've got two H's over here. And then we have, this one gave away. And, but we only have, so a total of 5 H's on the left side, but we only have 4 on this side. So if we put a 2 in front of this right here, now we're going to have 8 H's. And if we put a 2 over here on this side, we have 4 H's for the first. That's not right. That's not where I want the 2. I want the 2 right here. There we go. If I put the 2 right there, now we're balanced. We have a total of 8 H's on this side, and we have a total of 8 H's right on this side. But so notice what happened. It did indeed only donate 1 H plus to the NH3. It donated both of those, but the way that we accounted for that was by this big 2 in the front here. It just donated it to 2 ammonia molecules instead of just 1. Right? So the base did only accept 1 H plus. All right, we can assume that will be the case. So just keep that in mind if you're asked to write something like this, that you're only going to be moving over 1 to the base. And it should be pretty easy to recognize which one's going to function as the acid and which one's going to function as the base. Now, something else that's really simple to see once you get the hang of it is when you have a reaction like this. So we've got HF as aqueous, KOH as aqueous, and it's going to produce H2O as a liquid, and KF, which is aqueous. And so which one's the acid, which one's the base? Well, remember, our first rule was if we have an ionic compound, and this one's ionic because it begins with a K, and it contains the hydroxide ion, that will always be our base. So this is our base, this is our acid, right? And so when that happens, notice this H is going to come over here to this OH, and it's going to form H2O. Well, what's left? We've got a K and an F left. And so the K and the F are going to form an ionic compound. And what ionic compound will it form? Well, K, we go to the periodic table and we look at potassium, and potassium is in column 1. And so it's going to have a positive 1 charge. Fluorine's in column 7A, so it's going to have a 1 negative charge. When we swap and drop, we get KF, which is exactly what we see over here on this side. And we've got the correct number of H's and O's and K's and F's, so this one's actually already balanced. But this is what we can expect to happen whenever you have an acid combining together with an ionic base with this hydroxide ion in it. It's going to produce water and what we generically refer to as a salt. Salt is, of course, NaCl is what table salt is. It's a super common ionic compound. It's often one that we use as an example when we talk about ionic compounds. And so that term salt can be used generically to just refer to any ionic compound. All right. So let's see. We're just going to make a note of that, and we're going to consider that in the next example that's in the book. An acid reacts with an ionic base, to make water and a salt. All right, where the salt is just an ionic compound, and a salt. And like we said, that's just an ionic compound. Okay, so let's look at example 11.3 real quick. And following this rule, see if we can figure out what the chemical equation is for the reaction between HCl and CaOH2. All right. Let me erase this here just so it doesn't confuse us. There we go. And so let's think about that. It's we have an acid, hydrochloric acid right here, combining together with an ionic base that's got the OH, the hydroxide ion in it. So we're going to produce water and a salt. What is the salt? Well, if you remove the OHs and this H that's donated here, the salt will always be made from whatever's left over. So we've got a Ca and a Cl left over. So Ca, Cl. Looking at the periodic table, Ca is in column 2A and Cl is in column 7A. So Ca is going to have a 2+ charge. It wants to donate both of its valence electrons. Cl wants to gain a single electron to be ideal, so it's Cl negative. You swap a drop with that and you get CaCl2. So that's going to be the salt. Whoops, that's going to be the salt that's formed by this reaction here. And then you just need to look at it and balance anything that needs to be balanced. Like I see immediately the Cl here, there's 2 Cls, and so that means we're going to put a 2 in front of this. And once I do that, that's going to give me a total of 4 H's, and we've only got 2 H's here, so I'm going to have to put a 2 here. That's going to give me 2 O's. The O's are balanced now. We've got the same number of Ca's, so this looks like this would be our balanced chemical equation. All right, and these are really common, so just pay attention to that. Look out for those acids reacting with ionic bases, and if that's the case, the solution to the problem is basically going to be they make a water and a salt. And you can just put the water on the other side, and whatever is left over is going to form that salt, that ionic compound that's created by this acid-base reaction. Just to make sure you're getting this, I'm going to do the second half of 11.3 as well, because it involves a polyatomic ion. So I just want you to see this. H3PO4 plus KOH, all right? All right, again, we look at it, we've got an ionic base, right? This is our acid, this is our base, and we know it's an ionic base because it is ionic, it's got K in it, and it's got the hydroxide ion. So that's going to be our base based on rule number 1. And so these H's here are going to combine with the OH in that case, and they're going to form H2O. And then again, whatever's left over, in this case, it's a K and a PO4. Those are going to combine together to form our salt. So what happens with K and PO4? Well, we have to know our table on page 245, right? And know what the charge is on phosphate. And so you guys have memorized that. And so you know that phosphate is PO4 3 negative. So we're going to put a 3 negative there. And you're going to go to the periodic table and you're going to look up K, and you're going to see that K is in column 1A, so it's going to have a +1 charge. And so when we swap a drop with this guy, the 3 comes to the K and the PO4 gets the 1. So that's what's going to be made here in addition to the water, K3PO4. And then again, we just have to make sure it's balanced. We're going to need a 3 in front of this K here because we got 3 Ks on this side. That's going to give us a total of, looks like, let's look at the H's next. That's going to give us a total of 3 and 3, so 6 H's. And so that means we need a 3 right here. That gives us 3 O's and 4 O's, so 7 O's. Looks like we're balanced with that. Looks like we have the correct number of P's, so I believe that's right there. We just needed a 3 in front of the water and a 3 in front of the potassium hydroxide. And looks like we're good to go. All right, so super easy. As soon as you see that ionic base with OH in it, you know that you're going to be dealing with an acid combining together with a base that's going to produce water and a salt. Okay? All right, so try that out in your comprehension check questions and let me know if you have any questions about it.